This is the last slide. This is the last slide.
Oh.
Actually, this way.
Oh.
It's exactly this one.
Well, I'm not going to talk about that. We'll go to this one. Before I talk about two-way slab design with emphasis on shear, today is my last day of presentation, and I will be leaving after lunch. So there are two presentations I'm going to make today. One is concluding the design of a two-way slab. The other presentation I'm going to make is the kind of fire test that we did and what kind of a response we have been getting from the fire test and what kind of preventive measures that one would like to take. Those are the two topics. But before I do that, number of people are asking me questions. I came a little bit early compared to some of you asking questions, so that's what I was trying to explain. Obviously, the most burning question is with regards to aging. So in terms of aging, you have two broad categories. One is dealing with a specimen having ground contact. The other is without contact, non-contact. Those are the two broad. Under each one of them, I jotted down as he was asking, we have tested for water immersion, cyclic, this is why I brought this up today, cyclic type values, meaning we do both wet and dry cycling. And I did not mention it, I completely forgot to mention, the most critical response is due to wet and dry cycles. So I forgot to mention that. Then we have done the pH type responses. Somebody might wonder, where do you get pH in our kind of structural systems? Where would you get a pH value of 12 or 13? This is extremely important because the pore water in the concrete has a pH of about 12. So we always like to do this slightly higher than what we normally observe as a peak value. So that's why we went up to 13. And also, we have seen tremendous degradation of glass fiber under the exposure of high pH. Wait, it's a qualified statement. I want to qualify that by saying, if you use low-grade resins, that is the caveat. On the other hand, if you use a higher grade resins, we did not find the degradations that severe with glass. Obviously, you do not have any loss of area of the fiber when it comes to carbon. And no doubt, glass is inert material, whereas carbon will have a galvanic corrosion. It will form an electrical cell, and you get into corrosion type problems. While in fact, the aramid fibers, like your Kevlar, the bulletproof vest type fibers, these are synthetic fibers made of polymeric materials. They absorb a lot of moisture. So if you are dealing with a dry environment, it is okay. But if you are dealing with a wet environment, aramid fibers are not okay. We have been talking about glass primarily, and I have stated many times the E-glass is about 10.4 million psi. That's approximately 70 gigapascal, roughly speaking, plus minus. And S-glass fibers are of the order of 100 gigapascal. Okay. Now, let's talk about a little bit of aramid fibers. These are twice as stiff as E-glass fiber. They're of the order of 150. So why I'm saying is, if you are looking for higher stiffness, then you may want to go to aramid fibers, but they can be very expensive. Especially you can do that if you're dealing with a dry environment, not a wet environment. And carbon fibers, you have a variety of grades. You have carbon fibers that are 35 gigapascal, that's the lower end of it, all the way up to almost 1,000, almost one, yeah. I'm also converting in my mind while I'm talking. I'm more used to FPS units rather than your SI unit. So that is what the high-grade fibers, like I showed you, the 787 type applications, you have a high grade. And obviously the cost are going to be vastly different. One is a pitch fiber, the other is a pan fiber. It is a matter of how you process these fibers. And the fourth one, I didn't say much. Actually, I should have, are the natural fibers. I did a lot of work on them. I even imported natural fibers, in this particular case, jute from some company in Delhi. Bangladesh has a lot of jute, but I didn't get it from there. They couldn't supply it, but anyway, I got that from. All right. Then you have canaf fibers. You have many other kinds of fibers. Philippines have an excellent fiber. What do I mean by excellent fiber? Again, here we are talking about the durability, we are talking about stiffness, we are talking about cost. All right. Now I'll give you some relative ideas of what the stiffnesses and the cost of the fibers. I'll give you some absolute values first, then I will give you specific values, meaning you divide that by your specific gravity of a fiber. If you look at it from the specific property value point of view, you cannot beat a natural fiber. If you can somehow, I'll give you the numbers in a minute, if you can somehow arrest the degradations of natural fibers, which I believe you can. I haven't done enough work to affirmatively say it can be done, but that's why I didn't modify the fibers. I only used what I got, that type of thing. So that is the differentiation I want to make. As I said, we have many kinds of natural fibers. India has, I'm not saying India produces, but it has the potential to produce variety of natural fibers. The jute is somewhat of a medium grade fiber, but if you go to canaf, it is flax. India produces flax. Those are higher grade fibers, There is another name, another fiber. The Latin name is Morea koyangi. That's like the Telugu people call gongura type thing. I don't know how many of you know. That is another excellent fiber,
Hemp, sir?
Hemp is different. For a long time in the US, we are not allowed to use even the word hemp in a research proposal because that is related to your marijuana. You follow me? So what they do a Google search, and if they find hemp, it'll be thrown out, But now they're a little bit relaxing that. But hemp is also a good fiber. Let me say that. We did that work too. So, all right, let me now give you some numbers. Having said all this, the single fiber stiffness I'll talk about the higher grade fibers, like hemp is good, flax is good, canaf is good. Those three categories, families, have about 6 million psi per fiber. But I said glass has 10.4 million psi. So how is this better? That's where we use this specific gravity thing. Therefore, we call this stiffness per unit weight. Therefore, glass has 10.4, I divide it with this specific gravity of 2.8, 2.9. Here I'm suddenly talking about 3.5 per unit weight. Whereas hemp or canaf has 7, 6.5, but the unit weight is 0.6. Meaning the specific gravity, 0.6. So 6 divided by 0.6, suddenly I'm talking about 10 versus 3. Now, you got the drift of what I'm trying to tell you. So the natural fibers are really good if you can come up with some type of a coating. I haven't done enough. And also, another thing is, if you can somehow graphitize a natural fiber under high temperatures and pressures, that will be as good as your carbon fibers, the synthetic carbon fibers. You see, so those are the other that family of fibers I haven't discussed. But my grad student David Dittenberg and I wrote a paper on natural fibers, made all the comparisons, blah, blah. If you Google it, you'll find it. Believe it or not, we got about 1,700 hits on that one. That's one. I don't know why it is so popular. I think the popularity is coming from Europe. Today, Europe is saying that all their composites must be in a position to be recycled. Obviously, natural fibers are in the best positioned for recycling. And also, they are lighter. The specific stiffness, the specific strengths are definitely superior. So this is where probably, that's where the material scientists stop. This is where probably the structural people need to pick it up and see what you can do. Remember, the E values are lower, we know that, but what we need to figure out is come up with, to compensate for the E, come up with the EI value. That is where you really need to look at the nature and see how the nature's formations are in terms of the caves, in terms of beehives, all those kinds of things, and see how they're forming it. I'll give you a funny story, actual but somewhat funny. I did some work in the area of timber. I built over 100 timber bridges of different modern systems of timber, whatever. So I got interested in timber in that sense of it. I built one single span timber bridge that is 100 feet long, single span, all right. Then I came across an article in Australia. I'm sure there are termites that's infested with termites. Okay. So when the native material that's readily available is timber. So when they build the timber bridges, what have you, obviously there are drying processes for timber, which is a composite, by the way. I said that, but I like to repeat it. So, okay, there's a drying process, and then there is a curing process, right? They're not excellent, but they do have it. Today, I'm able to, in my lab, by the way, produce or modify timber as strong as steel. We won't go there, but let's talk about my anecdotal statement. So, they built these timber bridges, and
I think so in the US, timber is widely used.
Oh yes. We use almost 90% of our housing is by timber. Almost 90% of housing in. This business of concrete and steel are more recent phenomena. Recent, it's all a relative scale, isn't it? So now you people are finding the lack of durability of reinforced concrete. You see, now you're fine. Anyway, let me complete my anecdotal statement here, then I'll get back to a few other things I want to say about timber. Australia is infested with termites, and these timber bridges were, of course, partly eaten by these termites, but they're not falling apart. So, sounds funny, but the fact is, the termites figured out, you see how clever they are, the termites figured out what locations of a cross-section of a bridge they can eat and what they should not eat. So they ate those locations where the stress concentration, stress inducement is minimal. Okay, now how did they come to know, right? Okay, I'll give you my take on it. I may be wrong. How they come to know is, that's why I started out saying timber is a composite, right? And timber has two types of fibers. One is cellulose, the other is hemicellulose. And obviously, when I say it's a composite, it has a binder known as lignin. So how did they come? So when they are going closer to a high stress concentration and want to eat it, then that fiber snaps and hurting the termite. So they figured out, I don't want to go near that, and they probably know as I move towards higher concentration, I'm getting a bigger beating, therefore I'll stay in the zone where I can handle the beating. That is how, anyway, that is what I mean by saying you need to look at how the nature's formulation is. I got 2-3 patents just by using those kinds of concepts, actually. So anyway, that is the kind of a thing. Now, let's go back. If you look at the specific strength and specific stiffness, meaning whatever the strength, whatever the stiffness you have for the fiber divided by the specific gravity of the material, timber, I don't know how many of you know, timber, undried timber, green timber we call it, is about 55, 60 pounds a cubic foot. Put it in specific gravity term, between 0.9 to 1. Green timber. If you dry the timber, it is of the order of 0.5. If you dry it. I mean, you can dry it down further, but we don't want to dry it down. If you go below certain moisture content, it's going to become dry rot. So typically it hovers around 15 to 18% of moisture content. So that is where up to about 10% of moisture, the strength goes up, maybe even 8%. After 7%, if you dry it, will come down. So, natural fibers, if you can find a way to protect the fiber, you will have a fantastic chance. And there is really not that much to protect a fiber. Yeah, every fiber has to be protected, but you don't have to go through super duper efforts to protect a natural fiber if you are going to use it in dry environments. So all those fabricators, I will encourage you, you get good jute fiber. So all I said jute is a medium grade fiber is in relation to, with respect to high grade fiber like hemp and kenaf and flax. From that point of view, they are about 30-40% lower in a relative sense. That's all I meant, okay? So if somebody really wants to make rebar with a natural fiber and use the component only under the roof, not outside, that's highly doable. So anyway, so I thought that is another fiber you need to know, okay? That won't work outside environment.
Especially in the wet one.
In wet ones it will not work. I mean, if you don't protect it. But if you protect it, I do not see any problem of. Why I say that? All our bridges are subjected to high moisture content, high pH variations. We don't have any problem. I think if you remember, I showed you a slide. I rehabilitated many bridges in my state made of timber back in 1890 to 1910. That's 120 to 130 years old. So they would survive, if you can. Another major advantage, if we can somehow figure out a way to make the fiber, plant fiber, durable, you know what the major advantage is? Timber absorbs carbon dioxide and it retains the carbon dioxide. So your ECF, embodied carbon factor, is on the negative side as opposed to spewing out all this carbon into the atmosphere. And do you know, by the way, cement, of course, concrete is based on cement, right? Cements in the world today we are producing are contributing 35% of the greenhouse gases. 35, you think about it for a minute, 35% of greenhouse gases. Therefore, it's kind of time to look for alternate materials, you know. So
Steel accounts for 7%.
yeah, steel, again, in a relative sense, we in the US are one of the few that use more steel than concrete. Somebody like India uses 2, 3, 4 times more concrete than steel. Same thing with China. I've been there many times. Same thing with Southeast Asian. So they're used to this product, you know, so which is good. I mean, but if we can somehow figure out making a material that would cut down the greenhouse gases, that would be environmentally safe, and it's also going to be a natural product. And I want to caution you, when you grow timber at a higher rate of growth by some chemicals, then the properties come down dramatically. So please don't use those high growth timbers for structural purposes. You know, even for non-structural purposes, the fast growing timbers are not durable. You know, the classic example is, I'm living at this, whatever the place they call it here. This is less than 5 years old, made of low quality timber doors. They're creaking and cracking and falling. So that's absolutely not acceptable in a long range thing. You know why it happened? People just don't know how to cure timber, don't know how to select timber, don't know how to dry timber. You see, these are all major sciences, you know. So the reason I say that, I'm not trying to belittle anybody. Same thing is applicable to composites. If you don't coat the fiber right, if you don't process the composite in terms of the curing and cure rate right, then it will fall apart too, you see. That is, okay, now enough said. So another question they are asking me about this whole concept of balanced failure. Where did this limit state of 0.01 is coming, and why that type of it? I explained that, but there's nothing wrong in asking the second time or third time, no problem. So I said, for steel, if it is a 60 KSI divided by 30,000 KSI modulus, you are talking about 0.02. And if it is 0.03 there, 0.02 there, so the C balanced is 0.6. Whereas what they did to arrive at the quote unquote FRP balanced strain number, they didn't have any better direction. Therefore, they said, I'm going to keep that same 60 KSI divided by the modulus, that is a 6,000 KSI, that gives me 0.01. That I explained that before, and somebody asked me, I thought maybe I didn't make myself very clear. Sometimes I have a problem because I know it, I think everybody else knows it. that's a occupational disease, you know. So that is what is about. You know.
What is your take on the fibers produced by fungus?
Repeat.
What is your take on for the fibers produced by fungus? Like as you said, like
I got you. That's a very interesting question.
because in the masters I used it as a binder for my project. But instead of binder, if we use it as a fiber.
You know, the best binder comes from the saliva of a spider. You know, so they are analyzing it right now. Hey, that's good. I mean, you know, if you can rely more and more on nature about some of these things. I don't know how to answer your question, I admit, but I think that's very good if you can get that, you know. You know, the fiber coming out of the spider has the highest strength. They're not able to synthesize the molecular structure of that thing yet. Not only it has the highest strength. Again, when I say highest strength per unit specific gravity, I mean, yeah, always you have to look at it from that standpoint of it. Now, I won't get into it, but I just want you to think. How many of you today, or even till last 5 years, could even imagine we can modify timber, get a strength that is equal to steel? Think about it. So the revolutionary things are taking place in the area of composites, you know, and the seaplane they're calling. I'm told that Madras IIT, my alma mater, is apparently doing the seaplane related composite work from Chennai to Howrah, you know. That's what I read. I don't know all the details, but imagine how much of travel time you're cutting out of it, you know, how much of congestion you're relieving from the roads and rail traffic, you know. So these are the revolutionary things taking shape, you know.
So as a buyer on customer side, how can we ensure the quality of this resin of this product?
How can you improve use?
Designation or any designation for the resins. So we are in the buyer side. We don't know what resins they are.
Right. I'll tell you. And I shouldn't say I'm told. I saw several machines in this building, in this premises. One is DSC, differential scanning colorimetry. I'm trying to answer a question. DSC stands for differential scanning calorimetry. They said they got it, but they haven't opened it or something like that. They said that's one. I'll explain what that is, why you need, how you establish the QA, QC of the resin you're getting in 1 minute. That's one machine. The second machine is DMTA, Dynamic Mechanical Thermal Analyzer. You have it?
In practice.
You have it.
Yes.
Good. The third is scanning electron microscope. And there are other things, the Raman spectroscopy and what have you, we also use. CT scans we use, you know, the CAT scans we use. Okay, let me start giving you an answer. DSC very quickly, very accurately establishes TG.
Transition.
Glass, that you, if you don't know a lot about composite, you at least must know what a TG is. Without having a good understanding what TG is, you're just hot air, doing nothing, really. So, how do you we talked about TG, right? Okay. So, DSC quickly establishes the TG. What does it do? You keep increasing the temperature, and then this is a torsional thing, and then it will put out the stiffness. Torsional stiffness. Why do they use torsional stiffness? I told you 1,000 times in these 5 days, that is the shear modulus. The effect upon the bending, compression or tension modulus is not as great as that upon shear modulus. So DMC is essentially a torque-based machine. You don't need more than an inch-long sample, and then it does this at different temperatures, and it will put out what is the E value or G value is, and the minute it starts to go down, the G value, that means you can identify where it is beginning to at what temperature beginning to deteriorate. If you remember, I gave you a phase diagram of that maybe in my first day itself. So keep that, that's one thing. The second one, that's quality one, you know. The second one is a dynamic mechanical thermal analyzer that also tells you about TG. Okay, the third one, it is not necessarily the resin, but it is the resin system, which implies that you are cutting corners by having higher levels, higher percentages of filler. Okay. Again, I won't go into details. If you know the manufacturer, they would confess certain things to you, right? Okay.
Addition of calcium carbonate.
Addition of calcium carbonate should be limited to about, I would say 10, 15, no more than 20%.
Yes.
You know, now, once you go above that, not necessarily the resin, the properties are going to degrade. I can tell you some manufacturers confessed they were using up to 40% of calcium carbonate. So again, it is the resin system, not the resin. Okay. It may not be either one of the two. I'll give you the third one. Some of the other admixtures like the pigments or the shrinkage, other additives, shrinkage related or whatever, going to give you a problem. But no, even there's a fourth one, that is the promoters. How much would you see if somebody said they are, oh, there is the gentleman there, they said that they want to produce 12, 13 feet, I think that's what he said, of rebar per minute. Wonderful. How can you cure it? That is, how can you cure it? You use a promoter, right? So it would fast cure it. That will create a problem, you know. Some of you coming from the steel side, why do you, in the casting, cool it over a period of time? If you suddenly cure it, you're going to get a huge residual stress. That's exactly what is happening. So all these parameters play a role. Actually, if you think production of steel is difficult, this is much more difficult than steel. Your capital equipment is not high in cost, but high in its sensitivity. See? compared to steel.
So DMA is also similar to DSC, sir?
Right. Yes.
Both are one and the same.
Well, they're not one and the second. DMTA is a the rotational base, that is a temperature based. The DSC is a temperature based.
So even if we are given DMA, that is also reliable.
Oh yes, absolutely.
So I had somewhere DSC is more accurate and precise to rely on than DMA. Here DSC charges are more than DMA.
Again, this is where you're cutting into corners, you know. I cannot answer that really. Your conditions, I am not aware of
Both
them.
are reliable.
Both. Oh yeah.
So
Yes.
like gradation of steel, like we have Fe415 like that. Is there any gradation, some specification for this GFRP boss?
Oh, absolutely. We have. That comes out from the fiber and the resin. You know, when you talk of the gradation, you are talking about it from the strength point of view. Yes, we do have the gradations, and again, those gradations depend on the type of fiber you use and so on. Now, let's go to SEM, scanning. I won't go into CAT scans and other things, they're all equally important. But if you talk about scanning electron microscope, now we are having such powerful microscopes that you cut a cross section, you prepare the surface, you put it under the microscope. Glass will give you one color, resin will give you another color, filler will give you a third color, void will give you a fourth. Therefore, we don't have to sit there, find the area of it. The computer, apparently they have one something like that here. Wonderful, you know. It's doing that, therefore, I can tell you if the fiber volume fraction vis-a-vis the void volume fraction, the void volume fraction is higher than 1, 1.5. I would question the quality of that thing. And that depends upon the pull speed, that depends on the hydrogen peroxide that I'm going to use as a promoter. You see, it depends on, and also it depends on the resin type, you know. Yeah, I told you an anecdotal story. If there are 10 manufacturers producing 10 different vinyl ester resin, epoxy, you may get 10 different properties. That is why, remember the words, that is why you need to always standardize the process. It's exactly like cooking. You know, some are better cooks than the others. You know the rest, I'm not going to go into it, but that's exactly what it is. So, the resin chemistry is far more important than the fiber chemistry, because fibers don't, glass fibers, don't degrade unless you hit. We process the fibers at about 2400 degree F, that is roughly about 1400 C, roughly 1300 C, and nothing much happens unless it's chemically eaten away, you see. But on the other hand, it is the resins that create a problem. And one other thing I want to say and move on here is composites are very good at lower temperatures than at higher temperatures. You don't want to go 160, 170 degree F, like translates to about 80, 85 C, whereas you have no problem going to minus 30. We have done that. I tested composites using liquid nitrogen. They call it liquid ice, you know. So that's minus 40. No, didn't have any degradation at all. So you are more comfortable about it. There may be some degree of brittleness, wrong word, some degree of increase in stiffness of the composite due to the fiber. The resin becomes more glassy in its behavior
At lower temperature.
at lower temperatures. Yes, yeah, not at higher temperature. But having said that, educating you, I want to point out we have a class of resins known as polyimides that go up to, what is 720 degrees? That's about, I would say, 400 degrees Celsius. Operational temperatures, mind you. So we're talking about softening temperatures of 800, 850 degrees. So we do have, but they're very expensive. For the aerospace, the spacecraft type purposes, they do use these high temperature resin systems. Polyimides, IMIDES. So there are a lot of interesting things going on. It's a matter of how well, how good you're going to focus on going after it, you know. So you can Google my paper on natural fiber composite, and you will see that they have excellent. If somebody can come up with a coating, you know, that would survive the moisture ingress, or for that matter, the pH protection, then that is the best fiber. And there are the Singaporeans and the Chinese are working heavily in terms of bamboo fibers. Right now, they are. I'm on one of their universities. What is that called? Nanjing Tech. I'm on their advisory thing, so I have an idea what goes on with that part. Okay. So I'm going to. I've already talked about any other questions. I know you prefer to ask a question one-on-one. I prefer to answer it as a group. The reason is you feel shy asking a question, thinking that people think you're stupid. No, I mean no. In my terminology, no question is a stupid question. You know, it's just a matter of in what angle you are going to be viewing all this. That's about it. So the reason I explain it in a group, others should also know what is happening. Again, I have no illusion here thinking that I taught 27 hours and you all became experts in composites. I have no illusion at all. I'm stupid if I think that's the case. But on the other hand, you're exposed to different kinds of these things, what's going on, and if you have enough inquisitiveness, curiosity, you go and work on them. That's.
So is jute as good as you were saying? Like
Repeat, wood?
Jute.
Oh, jute.
Jute fiber is 30 to 40% less in terms of performance as compared to camphor.
Yeah.
So, is there any application of jute possible, or?
Oh, there are many applications that are possible, and yes. Look, the very first application, comes to my mind. All your automotive bodies are made of jute in Germany today. Jute or natural fiber. I shouldn't say jute, but yes. For example, all of them. They are no longer using synthetic fibers now. I'm not saying 5 years ago, 10 years ago. Today I'm saying in the last 3-4 years, there was a law that 80 or 90% of their bodies have to be recycled. And you can, of course, do a lot of recycling with glass fiber and what have you. We don't deny that, but that's much more expensive than recycling and making it amalgamate with the nature. Those synthetic compared to natural fibers. Yeah, that's one of the examples. There are many other examples. Another classic example comes to my mind is the children's playing equipment, for example, you know, in the backyard. Commonly, people in US have a lot of these kinds of playing equipment type thing. So that's another. And it's easy to form a jute fiber composite than a glass fiber composite. You know why? It is not as brittle. Look, why do you think the timber floors are so good? Because they have a tremendous damping capability. They are not brittle. See? So we are now mass manufacturing what we call CLT, cross-laminated timber. And we are building a 20-story timber building. 20-story. And another thing, I said it, I want you to appreciate it. Mass timber does not burn as one might think. A comparable steel section degrades faster under certain 400-500 degrees Celsius type condition. The eutectic point for steel is about 450 or something. Then it will start to change the phase of this material. Whereas, you know what happens here? It forms a char, and the char shuts off any oxygen moving towards the core of the mass timber. That's what it does. So we have seen that, we have shown that experimentally, what have you. I will show some of, I'm not going to show today timber, but I'll show something about the composites today, you know. Anyway, anything else? Yeah.
When any specimen is tested,
Repeat?
when any specimen, FRP reinforced specimen is tested, like a beam, so what happens is that it has the influence of, like, if we have to test the specimen after long duration so that the influence of the concrete does not come. So, but if you make the member over reinforced, then the strength of the final strength of the member will not depend on the strength of the FRP, but on the strength of the concrete. So, should we test the beams as under reinforced or over reinforced?
Wow, that's a loaded question. I have never thought even about that. That's a wonderful question. You see, our designs are mostly, so far till about the last 10 years, are based on first strength, not based on last strength. You have to really design it for the strength of that material, projecting whatever 100 years from today, right? I mean, it has to say, if I'm guaranteeing 100 years, what is my strength? So what he is asking is that if you test it over reinforced today, you get some strength. But he is presuming that 100 years from now, because the material gets partially eaten away or degraded, and he's presuming that that degradation leads to under rain. That's his presumption. This is the reason why we have so many knockdown factors, you see. I'm hoping that even about half of the strength of what you have today, 100 years from now, is going to be, that's the idea of having the knockdown factors. You know, this whole concept of knockdown factors is for civil engineers, not the aerospace, is only in the last 10-15 years. Remember, nothing before even people thought about it.
Like if we design an FRP member with different kinds of FRP bars, but we make that over enforced, then the final strength will depend only on the strength of the concrete and not of that of the FRP bars. So how will we differentiate between the two?
Okay, again, the final 100-year strength of concrete may be good, maybe not good. Again, that's a material property.
I'm not asking 1 year from now,
Uh-huh.
if you test two different kind of FRP reinforced members, they are over reinforced. So the final strength will depend only on the grade of the concrete.
On the strength of the concrete.
Strength of the concrete and not that of the FRP.
Correct.
So how we can experimentally differentiate between those two members? So we make them under reinforced.
That's a good question. We are typically presuming, by and large, concrete does not degrade in strength with time. On the other hand, concrete increases in strength. By and large is my word, remember. I'll qualify that in a minute. You understand what I mean? We have seen concrete, may not be after 28 days, after 35 days, it may not increase tremendously, but 5%, 3% increase in concrete strength we did observe. So do not presume that concrete should degrade with time, you know. Yes, there are scenarios under chemical plants or whatever, or due to excessive cracking from corrosion, they degrade. I understand that. But material by and large does not degrade. What happens really, what you should be asking me is, I'm designing a steel reinforced concrete beam as an under reinforced beam because the concrete strength keeps increasing for 10 years, 15, 20 years now, then would it become a over reinforced concrete beam? That is the...
If we don't consider this degradation or increase in strength, suppose the strength is static. So after 1 year, we are, at any duration we are testing the beam. It is not about decrease or strength or increase in strength. I am just asking that if you test an over reinforced beam, we will not be able to get the property of the FRP bar.
If it is an over reinforced beam, the bending capacity or shear capacity depends upon the concrete, not depends on
Yes.
FRP.
So should we make under reinforced beam for testing in the laboratory?
We did, I mean, but that's not going to reveal that's not going to reveal how that under reinforced beam is equivalent to over reinforced beam. You see, that relationship is an issue. Now I got your question. You see what I mean? That is the aging question. That is where I provided you with that elaborate, erroneous procedure of how to establish the aging part of it. And that's where the million-dollar question is, you see. I cannot reveal, I mean, I cannot correlate in a reasonable accuracy how to, you see, if I know how to do it, I'm in business.
I'm not including aging also. I'm just considering over reinforced or under reinforced, which is how, what should be our experimental
setup.
It should be over reinforced. I mean, okay, we prefer over reinforced. I prefer over reinforced. So it should be set up as an over reinforced beam. Period.
Sir, the question is, I guess, that in an over reinforced beam, the property depends only upon the concrete. Like the concrete crushes first. Then after the result, we will not be able to get the properties of the FRP bar in an over reinforced section.
What do you mean by you're not going to get it? What does that mean?
Analyze the properties of GFRP, FRP in the over reinforced beam. Then for testing, for the quality testing or the property testing of beam FRP bars, we have to consider always the under reinforced beam.
Sir, is the failure is in concrete or with FRP at failure's condition?
Repeat again.
So at the failure stage, whether it is from the concrete side or from FRP side.
Over reinforced, it will be from concrete side.
He's right.
Then that is what he is asking.
From
If we are over, even though it is over reinforced, the failure will be at the concrete side.
correct.
Then why we are getting it over reinforced?
Then we don't have to test to determine the FRP properties
So,
for over reinforced beam.
Instead of
over reinforced, we can increase the strength of concrete.
No. I'm saying that for testing purpose, like if you want to get the property of the FRP reinforced member, the property, the ultimate strength moment of resistance will depend only on the concrete, but not on that.
Ultimately strength on concrete, not on FRP.
Yes. But we want to test the FRP.
Well, that is the reason is
Okay, very, very simple. Is your FRP maintaining the original properties? Is your FRP maintaining the 60 KSI strength as a minimum after aging or not? That is, I need to maintain this in a guaranteed manner. If not, this whole thing will fall apart, even though it is over reinforced. That is the reason. See, I cannot deviate from this, because that the whole premise, assumptions I made, many of course, one of them is this. So how do you know it's going to maintain 60 KSI or not after 10 years or 20 years under different kind of environment? If this is guaranteed, you are absolutely right. At this point, I don't know whether I am going to be able to guarantee this number after 10 years or whatever. That is the reason we need to. It's an over-reinforced. It is driven by the concrete properties, no doubt. But at the same time, I need to make sure my minimum properties of FRP are maintained. Is that satisfied? Thank you. Good question. Okay, anything else? Good discussion. I know that generates a lot of different ideas, you see. You always learn from different people's ideas. Don't look at the short side of the question, look at the longer side of the question, you see. Yeah, so that's what it is. All right, so we talked about it. We talked about all this in terms of two different slabs resting one over the other in perpendicular directions, but the original Euler's equations, Euler-Bernoulli's equations, I should say, were like that without accounting for the torsional stiffness properly accounted for on the beam. That's what the slab is all about, and that's what plate equation is all about. So the direct design methodology, we discussed there are certain constraints. The most important constraint you must remember before you proceed with this methodology is what? Only good for gravity load. That's the most fundamental aspect. The second thing is they want to have at least three, both directions. Otherwise, the two-way business is not going to work. Okay. Like that, we created about half a dozen of those items. Here are the limitations. And the third thing is about the stiffness. Always it is related to the stiffness. Remember, for isotropic material, we said the A over B ratio is 0.5 to 2. But that's under the assumption that my stiffnesses in two different directions are same. What if they are not same? That is exactly why we have created this one. This means what? If it is not satisfied, I'm creating a weaker section, you see? So that EI over L business needs to be satisfied. The relative stiffness, that is the range. So, okay. So you must first check this before you do the other. But of course, there is a more accurate methodology. We went about it. I'm not going to run an example, but we know, we already saw that. So here, finding the statistical factored moment m sub 0 is what you don't have to find it. The code has already given you those numbers in a little simpler form. So they don't want you to make an error. So now then you distribute that moment. That's what we're going to talk about today. That factor in our case is 0.6 versus 0.4. So I will discuss that, whatever that is. Now you distribute the moment, positive and negative. What's that? Positive moment is at the center of the span. Negative moment is top of the span, beam or whatever. So then proportion, size and distribution of GFRP in both directions. So the direct design methodology, certain things we need to assume. We are typically assuming about 10% of the span length, which is an average value. Remember, about 10% is a good number, even though they give you a range. That is the critical part of it. Then shear check. We're going to find the shear at d/2, left and right. Where the slab thickness is not adequate, then increase the column size or increase the F'C or increase the slab thickness or drop panel. You know what, I told you many times, I would rather controlled increase to begin with anyway in terms of F'C. I would not dabble with the drop panels and things like that if I can help it. Remember the words. Divide the structure into equivalent frame bound by center lines, which I already showed you. There is that. That's what you have to do. And I'm not going to show you over and over again. I'm going to just move forward. So what is this factored moment that we are talking about is defined right there. That is the factored moment coming from the panels between, or the floor between the two contiguous column frames. So that is the moment we are going to keep working. L1 is the span, L2 is the center to center distance between the columns. I'm going to show you that one more times. Okay, so this is the span length, for example. This is your L2. Okay. So here are some other things. Select the distribution factor, positive, negative, that is given by the code. So they made your life very simple. Then, so find the thickness of the slab in a trial basis for moment shear transfer in the plates at the column junction. That's where that gamma factor is. That's where the gamma factor comes. So design the GFRP under bending to resist factored moments as per the step number 6, positive, negative values. Those equations are given. And then select the size spacing of GFRP to satisfy the requirements for crack control. And those are the 10 steps. Now, there is another methodology known as a more accurate frame methodology. I'm going to skip that. For now, I'll focus on this. This is again like your portal methods and what have you. They defined all these different things, including the torsional resistance of your beams. This is a very classic torsional constant equation. We won't go there. Now let's start the design of a frame only for gravity load. That is the direct. So I made that point very, very clear up front. Gravity load. So where would the lateral loads go?
Shear loads.
That is what we are talking, but maybe so, may not be so. If it is not so, then you apply the second methodology, that the equivalent frame. That's right. That's right. So the data given to you is 18-foot span, spaced at 14 feet, size of the bars is number 4, modulus is 6,000, 6,500 range. This is the area of the FRP, and that is the cover, and this is the strength of the FRP because it's only number 4. If my bar is number 6, I may be using 90 knot 108. If my bar is 3/8 inch, I would be using 120 or something. You see what I mean? So,
the FFU value is based upon this.
repeat.
Bar size.
How will you get this FFU?
It's given in the code.
It's given in the code.
Always.
Always. Or ask the manufacturer to give it to you. But you don't want to assume it yourself because it depends on the fiber volume fraction. For example, that's a critical item. Or it depends on how good the bar is made. It depends on the type of resin. All these factors. And more importantly, what is the standard deviation? You see? So that could make a big difference.
So the manufacturer will ensure the FFU will be at least this value.
That's correct. That is correct. That's what, yes, that's the idea.
Guaranteed tensile
Minimum
strength.
guarantee.
Right. Okay. So then we are further reducing it with this correction factor. So please note that the example is identical to a slab design example that I have circulated that handout for you today. And yeah, here is the handout. I'm going to leave the book with Professor Prakash. Okay, slab geometry. That's an error. That's 22, not 32. You remember we talked about 17. L over D should be about 17. Why are we using slightly higher value? Because both the top and the bottom of the columns are some kind of fixity, not 100% fixity, partial fixity. Okay, so these are all preliminary values that we are going to arrive at based on past experience, then we will cross-check it. That's why we are here. So we start with a 10 inch. So one may not have to go through all this. If you have a lot of experience, you can say 10 inch or 12 inch or whatever and get on with it. And I'm going to use this number. This is 328.1. There's no 1 there, please. There's a typographical error. So here are the self-weight. 10 inch is 125 and the miscellaneous dead load is that, therefore it's 140. The service load is given. Here is our very standard load combination.
For only gravity load.
Only for gravity load. Then you have to do all the other 5 load combinations as well as a check.
Sir, we have already assumed that it's only for gravity loads.
Yeah, but you have, when I say the others, you may have a dynamic system. Still, it could be a gravity system, see? Or you may have the ice load combination.
Yes, sir.
You see, or whatever those other kinds of, you may have, what do you call this, utility loads and all those kinds of things.
And we can neglect the wind load combination.
You have no choice. You have to neglect that because you can only do this if you have a shear wall. If you have a shear wall, there is no wind load effect.
No, yes.
Because the wind load is taken by the shear wall. So it's 328, that number comes in this example over and over again. So there is that 328, that is your m sub 0. Therefore, that m sub 0 you can see, this is what? 328 times 14 is a uniform load, that is your span. Okay, so here is the factor, a very, very important factor. What is this factor? Of slab moment transferred to column. That's given by the code. So that makes, imagine, I don't know how many of you do these high-rise building designs, that saves a lot of work. Okay? Now, if you don't want to use that, you can run your computer thing. This is on the conservative side. So if you run a computer thing, the factor for slab moment may turn out to be 0.7, 0.75. That's not unusual, but that's a conservative number. So please see here, this came from the code. Look here, live loading patterns. You as designers, you all know for the alternate moments, you'll get a maximum positive moment. For a contiguous thing, you get a maximum negative moment. That type of a thing is standard, very standard influence line based concept, right? Okay. So they further went ahead and gave you this. Look at that. So for a scenario like this, factored moment envelope is, for this scenario, is given to you there. So the max moment interior is about 2.7, for exterior 3.8. In the positive side, it is 6.0 on the negative side. So they gave all that to you to make life easier. So the unbalanced moment now is an equation from the code, that is 8.10.7.2. 0.07 dead load, live load, and another live load component. So this is the amount of moment, MSC, that is called the unbalanced moment. We can go, you want me to stop? I can stop and we can have a, it's 11:30. Huh?
We have a break for 5 minutes.
Oh, sure. Yeah, let's have a break for 5 minutes. Yeah. Thanks. Well, stop, no problem. 5 minutes, yeah. Take a break.
And DM, the moment distribution method in steel design is much simpler.
You see, another reason why they guide you here, they'll keep you
over, sir.
Okay.
After the
What diameter?
concrete,
What diameter
I have to test it
you are
in after that, thermal and durability skills are so studied.
Okay.
Usually it's 4
Okay.
mm.
As my professor statement, he
Guarantees to be given by the manufacturer. All these are very important, you know. We don't even second guess a manufacturer, for example, in the US. That is why we call this a minimum guaranteed strength. We're not talking about a maximum guaranteed strength. We're not talking about an average strength. We are talking about not only it is a average minus 3 sigma, but it is also something more you remember I told you 80% confidence values of the 95th percentile sigma. So that tells you essentially you are talking about on an average 60% of your average value. So therefore, if my average is 100, you are guaranteeing 60. If you want to grow, the manufacturer should take the lead in guaranteeing the minimum values. Okay, I'm going to wrap this up because of the time factor. So this is the slab moment, unbalanced slab moment. You remember I showed you the slab?
Yes, sir.
So where would the remaining part go? That has to be resisted by the columns and the beams, right? So before I can do that, what is the unbalanced value? So these are the kinds of things that the code has essentially defined for you upfront. So that is the definition of the equation for the unbalanced slab moment. And this MS, the quote-unquote unbalanced slab moment, transfers flexure and two-way shear into the column. And that mechanism of transferring value is right there. So you find the unbalanced moment and how much is transferred? Gamma F, and there is a equation given for you for gamma F, and it's given to you. I'll show you again. So okay. So that fraction is 0.6. Where did we get that fraction? As he was saying, there is that fraction. That is again conservative value, but given by the code. Okay. So we're going to start using that fraction that goes to the interior column. All right. Now, how much is the effective width of the slab, like a T-beam like thing? You remember? And that effective width is C1, that is 24, H over 2 and H over 2. We started with H is the slab thickness. That's the very first thing. Either we had come about it with reference to that preliminary L over 22, or you make a guess at it, you know. So one way shear check. What is the shear? It is, this is the shear. That is the shear. And that is a function of P. This is essentially PL over 2, right? What is P? W11 L2. That is your P value, yes. Correct? So that is the shear. And the effective depth is total depth minus the cover minus the half the bar diameter. That's what you get. Then B0 for a square column. This is a plus, not a multiplication sign. I put it right there. So that is the perimeter of that B0. And that B0 is 2 times, it is a square column, C1 and C2 are equal in this particular case. If it is not, you put an appropriate number. That D is the depth of the, effective depth I should say, of the slab. Two-way shear. These are now fairly standard computations, and we keep using this 0.6 and 0.4 over and over again. This is the shear. Essentially, what is the shear? It is, we have established that 32.8 in the previous computation, and we are subtracting the perimeter based shear magnitude, and that is my total ultimate shear. And we find that the slab shear stress is V over BD. The B is that opening is 4 times that C1 plus D or C2 plus D. That is that 131. That is the effective depth. That's about 70. So there is a modification beyond this to make the computation more accurate, and that modification is adding this component. That component, from my experience, I can tell you, is nearly negligible. You don't have to complicate your life if you want to simply neglect it. And you see the VUG is 71 70.3, while the total value is 71. So that is that small. Typically, again, we have a lot of cushion here, and you will see when you are going to make a check and a balance, my resistance value is much higher than the induced value of 70.3. From the minimum values, we already gave you these minimum values, and now you find the minimum spacing, and the code is saying from the shrinkage temperature point of view, the minimum spacing is either 12 or 30, and it should not be greater than the minimum of the two. And this is another equation. The code is saying 0.2 divided by your 0.392. So that is how you get the spacing of your bars. The max space ensures the crack width, and there is a procedure for that. So here we are talking about the negative region, meaning over the supports, over the columns, over the beams. So again, AFB balance is 0.2 for this case. We have already computed that. So the reinforcement minimum required is this is a very standard equation, that's 0.4 inches. So we are now trying to find the MS value there. This is a cracked section with a 10% of the effective depth as the uncracked zone, and based on that 10% or 10.3% of the uncracked zone, the section modulus of the cracked section is 1/3 BD cube, where D is 0.13 inches. That's what times D cube. Yes. So that's what we're talking. This is the AD square effect, and for the cracked section modulus, all this computation, we have done this before, that's why I'm not going over it in any great depth. That turns out to be 45. Again, please note, just like I told you earlier, this first term contribution is negligible. You can avoid that. And this is the sustained bending moment. I just ratioed it. This is for the factored load. This is that is the dead load moment. That is the live load. The factored ratio is 7.7. And the stress in the GFRP, MC over I, MC over I. M we just computed as a sustained moment, and that is the conversion of the unit. That is the D value. I value is 45. So S max given by the code, the spacing 8.63. This is a very standard bond factor we are using. Is much simpler than the one in steel related bond factor. Steel is so very complicated, unbelievable. So you got that max spacing. So number 4, GFRP at 6 inches will satisfy the crack width criterion. So we do another several checks here. As you can see, I want to point out that the stress is 16,558 psi, and that is the check we are making here. As you can see, it can take, this particular system can take up to 67,400. If you substitute all the values for 0.28 inch crack width limit state, substitute EF is 6,000 or 6,500, and these values which we computed earlier, this is 0.106, whatever this I computed earlier. Oh, there it is, 1.12, the DC value computed earlier, all that will result in, which is far higher than the amount that is induced from the external load, therefore we are good. So that is how you go through this, and ultimately the spacing that we came up with earlier seems satisfactory. So now we are talking about deflections. So any deflection, you know what that is? That is your WL4 over 384 EI, but written in a moment form. So if you multiply that with the L square over 8, you get exactly your W5 over 384 written in a moment form. And we have positive moment, and these are the two midspan. I wrote it here. This is the positive moment, you call it. These are the two end negative moments. That's what we have found. So the cracking moment, MC over I again, that is the cracking moment, corresponds to the stress due to rupture. If you turn that around, FR is MY over IG. I know what my FR is. What's my FR? You remember? For concrete, 7.5 square root of F prime C. That is the lower bound. Remember, you normally get about 9 to 12 square root of F prime C if you run the test. Again, the lower bound is 7.5. Okay, so we found that all that the service moment value, again based upon the ratios, found the M sub U. This is the one we found way earlier, 147, and 14 feet is the width of the T-beam like effect that I talked about, and these are the cracked column. The panel moment live load is live load. You remember the 100 feet? That's your P or W, L square over 8. That is the width of your panel over, like a T-beam effect, over the beam. Longitudinal span column strip live load moment is divided per width. That is your moment per width. So M1 is, this is the equation by the code, that 0.77 is the factor they call it, 0.65, that is the 44.8, this is the strip width. So anyway, this is how you find your M1 and M2 and M sub M, and you substitute it in there, here. Those are the moments you substituted there to get your deflection values. This is for the, if you remember, this is for the eye cracking, and that is dependent upon these moments that I just described. And then you can find the short-term and the long-term deflections, again based on 20% of the sustained live load. What is eye cracking?
You can also count that formula, sir.
Huh? Oh, that's given in the code.
Eye cracking is equals to I gross upon 10 or 12.
Yeah, you here again, you can use some of these in your...
Simplify maths.
That's what it is. Okay, so here are these sustained stress checks from the sustained moment values. The sustained moment value is based on 100% of dead load, 20% of the live load, and that is the sustained stress that I'm going to be using in my next slide. So here is the moment capacity check. That is your K factor based information. So we found out that this stress in the GFRP is much higher than 124 KSI as opposed to 29 KSI. So the rupture control or the tension control. So we had to redo this particular design, and we did that. Then we have a one-way shear check. Then I have a two-way shear check. Okay, and one-way, the difference between one-way and two-way shear check is the resistance. Please look here. The resistance offered by the cross-section, that equation is slightly different from the resistance offered by two-way check. It's all twice. This is 0.8 That's 5 for one-way shear. That is the equation given by the code.
Here we had to reiterate the.
Yeah, but here the magnitudes of shear under two-way are much lower than the magnitudes of shear due to one-way, from the induced stress point of view. I think that essentially concludes a design. All these steps are given to you in the handout for you. I breezed through it. The reason I did that is because somebody wants to hear a little bit about fire. So if somebody can open, I don't know where my fire, oh, you're there. My fire presentation, I'll very quickly go through, then I'll open up for some questions. So if you have any, this particular example is well laid out in that booklet, and I'm going to leave it with Mr. Ghosh, and he can, in the next few days, he can share that with you. Is that my fire? That is durability presentation. Look it up under EPRI, E-P-R-I. You want me to look? I cannot see well, so if I come close, I will.
Alkaline environment, this is different.
No, that's different. Durability, intro to FRP, only response of FRP. Yeah, the response of FRP.
Utility poles and wildfires.
That one. Okay, I'm just going to give you a very broad brush presentation. If time permits, I'd like to give you, I'll give you another modular housing presentation very quickly. I'm going to go this very, very quickly, give you an idea what we do with these complex scenarios. So, first of all, I want to say, I'll show you some numbers. I want to say that we develop composite utility poles that are about 20 inches, 24 inches in diameter. The central message of this is that these poles resist forces up to 120 feet height. That's the first message. So some guy asked me, do you use 120-foot high poles for your street lamps? I said, wait a minute. I never said I use that for a street lamp. That is for high tension transmission tower replacement. You get it? Sometimes, I assumed already he is going to correlate my 120-foot statement to a high tension transmission tower. He did not. He immediately asked me, is that for a street lamp? Do you understand the message? So that's what I mean when I say everybody knows what I'm talking, therefore that's my fault, not his fault, All right. So what does that mean? 120 feet high transmission tower, the utility pole. It has 3 or 4 implications I'm going to tell you. Number 1, of course, it is going to resist forces, wind forces, tension forces, with snapping of some wires, non-snapping, you know how they do the design. It has to resist all these forces. That's what it does. Number one. Number two, it is probably 1/4 the cost of your typical transmission tower, what we call lattice structures, you know, it's number two. You call lattice structure? Okay. Number two. Number three, I can erect it in a day. Number four, it is so lightweight. In New York City, I wish I had the slide, I don't have it here. In New York City, 2 people carried a 60 or 80-foot pole to put it in their backyard because the crane wouldn't go through their doors and what have you. So the flexibility for installation is the issue. Okay, but the punchline, most important punchline, is fire. I will show you some slides on fire. All your steel transmission towers melt. Here, I will show you some numbers. We burned this at 1100 degrees Celsius for 3 minutes. We still did not have any reduction in the properties.
1100 degrees Celsius.
See, you will see some of that here. Okay, that's a brief. I can go on and on, but I won't. I want to wrap it up because if time permits, I want to show you something else. My passion is about housing, low-cost housing for needy people. Anyway, let me finish this. And if I saw it here. Okay, number of wildfires, U.S. wildfires. You see, 30,000. That is how it looks in the field. Very dangerous, billions of dollars of loss. Composite material advantages over conventional materials. Here our goal is to understand the performance of the pole under wildfire. What is a wildfire? First I need to define that, right? A wildfire, you have one kind of intensity at the ground level, you have a different kind of intensity at the top, and some third kind in the middle. So the EPRI, Electric Power Research Institute, defined that all these fires are moving fires. They defined a wildfire to be sustained by a structure is 1100 degrees Celsius for 3 minutes. And then it will move on.
Yes, sir.
Okay. Now, so what are the issues? Nature and characteristics of the wildfires. You see that? What is that telling you? So sometimes you reach 1100, that's what, not much, but like instantaneously hits 11 and moves on. And that is on the vertical axis. On the horizontal axis, that is the time. So this is defined by EPRI, Electric Power Research Institute. The temperature ranges they're finding from their field measurements are given to you there. Anyway, these are fire severity categories. I won't go there, no need to go there. Here are variety of test procedures that ASTM suggests. There are many issues that one needs to, I won't go through all that, but somebody was asking me yesterday, that's why I put it up here. The most important test is a corner testing. That is the one. Here we have to take a full-scale thing. Of course, another important test out of this is tunnel test E84 and E119. We have to satisfy these two as a very minimum. And there are many others not quite as critical as those two. There we go. E119 test, corner fire test. Fully constructed and exposed to 1260 C for 8 hours. That's called a corner test. How long, how much will it survive? What is the remaining strength? Those are the issues. Test ends when unexposed side reaches a threshold value, and that number is given. This is one kind of a test. That is the fire shield. What you are looking at is a fire shield. They have the. This is a company is developing its own test procedure under a full scale. So there are certain things about the fire shield, maximum temperatures. You remember the 1100 magic number I said? What is the energy that is put out? All that. Look at the TG value. We all keep talking about it, how the TG is going to dramatically drop. Look at also, please, the roughly the TG temperatures. They are around 80 degrees Celsius, around, somewhere around there. How do you improve the fire resistance? What is the effect of fire protection coatings on the residual flexural strength? Use of flame retardants such as the aluminum trihydroxides as a filler, halogen additives, use of phosphorus as a retardant, and intermittent coating. The first three are the additives in a resin. The last one is external coating. On top of it, we have a fire shield. So there are three different ways we want to protect. This is the SEM view, layered fiber architecture of a composite. And let's look at the implications of it before and after fire. Obviously, that's before the fire. And as you can see, this is one layer, one laminate type thing, if you want to call it. This is another laminate type thing. So you have this alternatively. That is the cross section under SEM. So we torched it.
So if you are mixing this type of material, fire-resistant material, to enhancing its capacity, maybe they may have some side effects. They are causing voids or something. This chemical.
Definitely, you lose some strength. There's no question about it. We know that. So instead of having your is 0.01, we need to reduce that to 0.008. You know, something like that. This is the compromise you have to make when you're doing a design. See, we recognize that, and what I want is, that's my technician there. Wonderful technician. I lost him because he retired, but wonderful guy. So this is a sandwich composite, and that's a 1/4 inch sandwich. That's a balsa wood, and we have about 24. We call it. We talk about it in Fahrenheit. That's about 11, 12, 1300. So my message to you is, this has about 40, 45 layers to make a 1/4 inch. I was asking somebody this morning, or yesterday, right? Yesterday, they were using 45 layers. You know, that's what I was, yeah. So that 1/4 inch has 45 layers of 24 ounce per square yard composite. And you know what? It took us adjusting the flame. We have certain standardized measures. So, in terms of testing, we put an acetylene torch about, say, 6 inches from the surface, and for every layer took approximately 10 seconds of it. So the total, it is about 26 minutes, before the fire reached the core material. So that is how good composites are in terms of fire. Another thing, I have a different core material than balsa wood. In this case, this is a carbon foam. The message here is, as a torch, that is about 2200. After about 4, 5, 10 minutes, that's my IRT, infrared thermography. The other side is still 62 degrees. You can keep your hand on there. This is after half an hour or whatever, back side of the panel. So the thermal resistivity can be controlled depending upon the foam that you're using. Of course, we use a carbon foam for some other reasons. Never mind, whatever the reason. If you use the right kind of a core material, you can get that. Incidentally, I didn't say it. This particular one is we had to test it for the destroyer class of ships, where our role was to build the deck house, or the top part of it, keep it lightweight. This is a corner test, I told you, E119 type test. And again, we tested real fire, 10 feet by 10 feet by 10 feet, and it has to survive a minimum of 3 minutes. A minimum. And we have to worry about smoke, toxicity, and those kinds of things. As the fire goes on, these are the chemicals released. We want to make sure that they are within the parameters that does not create carcinogenic effect. So, fire performance evaluation of 4-inch thick load-carrying composite wall. I did that for my, we built a local school, somebody built, not me. I volunteered to provide my panels, and before I provided, they wanted me to test for fire, and that's what we did. And again, we satisfied the requirements. This is a composite, prefab composite panel, satisfied the requirement. Again, the very important test when it comes to fire are two, E84 and E119. This is E119. Of course, we have other things like opacity and the visual thing and what have you. Those can be exempt, but the two are E84 and 119. Fire performance evaluation of a 4-inch thick load carry. Yeah, I just talked about it. I won't go into a lot of details, but so this is the wall that we have installed in the school. This is the E119. That's our panel that we tested. So we developed a multifunctional, non-load carrying, load bearing. So the ignition temperature is 70 seconds. No visibility, that the opacity I was talking about is 160 seconds. Only that's almost 3 minutes. After that, you cannot see. So to escape, I mean, So up to 160 seconds, you can see and get out. A lot of people don't know it. In fire, the deaths are not due to heat, but due to toxicity. So various flame of exposed surface, after 11 minutes, there is a standard for it under the E119 flame of joints. After that's a critical one. So they have standardized that stuff. So implications of the above test for the utility poles is fire performance can be enhanced using the coatings. Phase flame burn occurs due to intermittent coating and layered fiber construction. That's what I told you, 40 layers of fiber delays it up to 30 minutes. Typically, the fire ratings are based on half-hour rating, 1 hour rating, and that rating in concrete building depends on the cover, clear cover, like a half-inch cover is 15 minutes, 1-inch cover is half hour, 2-inch cover is 2 hours, things like that. That's what we are talking about.
What is fire rating?
Huh?
Fire rating.
Yeah, I mean, that would tremendously enhance. Again, can you, what is it? Fire, think of it like this. Some kind of a Band-Aid. Leave it there. Of course, the material has to, you know what a Band-Aid is, right? So we wrap around it. That's a barrier.
It gets burnt, but protect the inner core.
It won't be easy to get it burned. It'll take a while before it burns.
Yes.
So, in other words, it's not like a paper will burn. You have to have a sustained fire before it burns. Okay. This is a double wall pole. I won't go there. In conclusion, this study has identified FRP burning as a phased process due to layered fiber construction, even without intermittent coatings. This multi-stage burning process appears unique in the fire behavior. Utility poles are able to survive general fires, and in conclusion, we can see that this will help the utility industry to use the FRP poles.
Sir, what is the cross section of that utility pole? Is it a hollow or
it's hollow?
Hollow.
It is hollow. It is. I have several cross sections depending on the length of the cantilever pole you want. They are 12 inches, 16 inches, 24 inches, and 18 inches. Typically, the cross section is for lower poles about ½ inch. For higher diameters, it is about 3/4 inch.
And it is also layered.
Oh yeah, all are layered. And as the thickness increases, the number of layers increase.
So how can you correlate that to FRP bars? These results are
All I can say is if I expose an FRP bar, for example, say the FRP has so many things, if I expose them to a fire of 1100, so it is going to take, let's say the 1/4 inch bar, as I said, say 40. So each layer is 1/160 inches thick. Right? So all I'm saying is 1/160 inch thickness is 10 seconds to burn through. Now your ½ inch bar, make it a 1/4 inch, will take about roughly 30 minutes. That is without the concrete cover. With the concrete cover, you get a better value. Okay, so that gives you a quick presentation on fire.
So for 12-inch diameter of your utility pole, you just said that the cross section was ½ inch, right? And it goes up to 100.
Not cross section. Thickness is half.
Thickness is ½ inch. And it goes up to 120 feet high.
No, I didn't say that. The 18-inch and 22-inch ones go up to 120 feet.
Okay.
The half-inch ones go up to, let us say, I don't know, I don't remember now, 60 or 70 feet.
Right. So, even for the 22 inch and the 18 inch and the 22 inch, you just mentioned that it's 3 inches to 4 inches in thickness.
3/4 inch.
3/4
Means
inch.
0.75. Yeah.
What's the the base that you've installed for it to resist such high forces?
Concrete.
Okay, you've installed concrete as the base.
I didn't want to get into a lot of details. You know what? Not only I installed concrete, I used the guide towers to make it a self-stabilized unit. Guide cables. What does that mean? You know what that means? That means that I am preventing the tilting of it by tying down the guide cable onto a very thick concrete foundation platform. Therefore, I'm using as little a footprint for it to be stable. Did you get what I said? There it goes. I'll show them in 5 minutes. There is another presentation here on Ollie.
Ollie, yes, that one.
This is on housing. Okay, this is kind of my passion. Okay, the reason I say it's my passion is, I just told you, I am able to develop modified wood of a higher grade, and some people, industry guys, want to come and talk about it. This is what I told them. If you are not thinking in the future about how to utilize the modified wood for housing, please don't waste your time. They're going to see me on September 15th and 16th. It's a great passion for me. So these are sustainable buildings we are talking about, right? I won't go into a lot of details. I'll just pass through. Okay. This is the FRP modular building. And there we go. That is my natural fiber panels I generated. So what I'm telling is, we are talking about the green composites for energy efficient buildings. There is only one of the 8 points, or in this case I only showed 6 points, that we need to be worrying about in terms of an efficient housing. One of the 8 or 6 points is the material. It's only one. There are many other issues that we need to bring in to make it more energy efficient. Okay, I'm going to talk briefly, breeze through some of the aspects. I won't delve into it. Each issue is a big topic by itself. All right, first one is, you want to have a durable, strong, stiff composite panel made of natural fibers, natural resins with 10 times lower embodied energy. That's the first one. The second one is the modular panels with built-in, I don't know, you know, trom wall concept or not, I won't go there, but you need a special wall from the heating, cooling. All that means is you're going to draw the geothermal energy. How do you draw it? Not by a pump, by a convection principle you draw that. Anyway, I'll leave it there, but that's another one. The third item is the sandwich paneling concept. You saw that there. That is the sandwich. I have a shell at the left and right. This is the trom wall concept I just briefly mentioned. And at any rate, then I have the modular panel with your solar panels or whatever. And then we're talking about smart windows and doors, you know, what we call micro blind. You know what that means? The high-end Benz cars, high-end, not low-end, have glass panels and the car doesn't get heated up inside. How? What they have is a glass panel with a very finely etched surface which
Reflects.
shuts off the heating spectrum of the light, only lets in the cooling spectrum of the light. So we have panels like that.
Projections at micro levels.
Yeah. I don't want to call it projection, we call it etching. You etch it in a certain direction. It's like I talked about boards. Sort of the same. You have to have a proper angle, you have to have a proper depth, you have to have, you know, all that kind of. That's why they etch it in the manufacturing itself. Anyway, forget about all that. What that implies is you can get a window pane for you, especially for India, that will be angled in a manner to send only the cooler part of the spectrum reflects out the warmer part of that. That's the principle. Anyway, that's another. So then, a roof garden, is it?
Yes.
So these are the ones we incorporated. Okay? All right.
Sir, won't the roof garden make the fiber damp?
You see, we have special plastic fabrics that would not let water go down. On the other hand, do you know water is the best insulator? You can't get any better insulator than water. So any dampness is going to be shut off. And do you know that 30 to 35% of heating or cooling requirement is because of the roof. 30%, think about it. So if I can control the temperature, I'm saving not 30% because of other losses. And even if I save 20%, that's a lot of saving, right? That is the thing. So same thing with human being. They lose a lot of heat for winter from the head. That's why everybody wants to cover their head, you know, without realizing why they're doing, but it looks good, sounds good, saves good, so therefore I do it. You know, that's what it is. Okay, sorry. So here is the modular concept. I got a patent back in '79. That here are, anyway, I won't go into detail, but that's a modular concept. And the beauty of it is, here are the modular. So these come up with various prefab, various functionalities, like you have conduits, for example, you have connector details, another example, you have joints in a manner that would transfer the shear forces, all that good stuff. And the windows and doors are fit because you just shovel it in, you know. So you can see how I can control even the colors. So I can get a variety of colors, and here is the foam core. Here is a building we built in 1992. Looks exactly like that today. Here is a pultrusion process. with foam. This is a polyurethane foam core. You can have many different foam core, but this is one of the many. That is how we built that building. That's the pultrusion process.
On the natural compost.
Yeah, and now we can think in terms of having these openings. That's what we are doing now. And this is the carbon foam, low-grade carbon foam panel. A variety of things, but this is that school building I'm talking about. That's where we did. You can see I can get any color I want. I can get a brick effect, Adobe effect, smooth effect.
Yes.
Intertech is the one that's helping us do all this work. We did some work on rammed earth. This is only good for rural areas, not for urban areas. I built the building in Alaska, and there was about 7.2 earthquake, about 50 miles, the epicenter, and it survived. That is the Alaska building. How you do the rammed earth, I won't go there, but the message is, it is so extraordinarily heat resistant. That is the message, or cold resistant, whichever the way you call it. These are some of the details about that. It looks good. It's not an inexpensive thing, I admit, but not for everybody. It's only for rural communities where you use the local material. That's the word.
Sir, the foundation is a concrete.
No, it's all rammed earth. It's all rammed earth. We learned this from Chinese. There are rammed earth buildings even in India, but that's only in the Kashmir, Nepal region, and they call them tulos. I visited one of the tulos that was built in year 600, 20 or 21 in that range. Functional tulo.
Is there any damp-proof for this basement?
Yes, they do have. Yeah, that's very important, very important. Or else you get the mold problem. There's a beauty with the composite. Composite never builds up a mold, you know. That's a different topic. I did some work in that area. Okay. I won't go there. These are all different. We always, as much as possible, money given, we always do a post-evaluations of these structures, because they're all different concepts. We don't know what's happening. I can sit here and talk, but the proof of the pudding is how it is doing in the field, you know. So this one, I thought this as a, anyway, I thought this as a video. This is built in, I forgot, few hours, that modular building.
The master effect of that will remain the same as in general concrete, I think, in the wall. For the appearance point of view, marking it.
Yes. You don't, correct. You don't find any.
Swelling of the whitewash will take place.
That's right. So we are now working on geopolymer buildings. I just got some dollars to do that, and that is the building we are going to build about a few miles from my office, and we are going to let needy people occupy it and then test it for a variety of things. This is just one of the several tests we are conducting. That's a geopolymer panel. That's the point. Geopolymer panel. That's the building. Here is some of the factory-based, that's a calcium carbonate we are using. See, when your economy is advanced, you want to sound sophisticated, right? You want to. Okay, good. But with that, you're also generating lot of waste, lot of recycling. So we are working on carpet recycling. That's what we are doing that. I won't go into detail, but that is we recovered the calcium carbonate, which is the backing of the carpet material. We are reusing that recovered in a pultrusion process, and we did that. We got as good a results as virgin calcium carbonate. This is the insulated sandwich with the discarded foam core. So where is the foam coming from? Discarded mattresses. We discard 14 million mattresses every year in US. Where would we bury it? So that's what we are doing. We conduct the thermal conductivity tests all along, and we put that in the wall floor panel that I showed you in my earlier slide. So the foam in here is that discarded mattress. That is the location where we are building. Oh, those are the conclusions. But that concludes my presentation. A broad brush presentation, a lot of detail. Many PhDs work on these kinds of things. So this has a lot of theory behind it. I just showed what appeals to people, not the theoretical part. That doesn't appeal to. That's a big, big drag on people's time and effort.
So have you worked with thermoplastics in this foam?
Have I worked with?
Thermoplastics, like PE, you have your polyethylene.
Oh yeah, we did.
These are
We did.
using the PE and
Oh yeah, yeah, we did. You know, in US, we discard 20 million railroad ties. What I suggested was, instead of trying to bury that in the landfill, we take the beat up tie, is 20 million a year, mind you. Take a beat up tie, wrap it with a fabric, and then all the thermoplastics are recyclable. And we recycled it and installed it. I don't have that presentation here, but yes. So, of course, you have to characterize all these things. These are not simple and easy. It's a lot of work, you know. So, I mean, a lot of preliminary work of how you characterize, how you are going to manufacture and all that. But we did. And that's where we have applied it. We have, I don't know how much you know, about 75 to 80% of our plastic consumption is thermoplastics. Only 25% is thermoset. And thermoplastics are highly amenable for recycling. And we wrapped the old tie and then heated the thermoplastic as like a bread dough, and then we poured it in, and that's what we did. There are many other recycling applications, but this is appealing because you're suddenly talking of 20 million ties a year. So I enjoyed working with you all, and if you have questions, please don't email me anything till I return back. That is the 24th of this month. So then, I mean, I'll be able to respond immediately, or I'll ask somebody to respond on my behalf. Otherwise, it may be buried. I get 200 emails a day, so I get buried. I don't want that to happen. Thank you all.
Thank you so much, sir.
So, is there any material for GFRP that we can recycle and remanufacture for it?
As I told you, any thermoset based material is currently not recycled, but we can recycle it. I'm getting a patent on that.
Yes. But
how do you recycle it? That's the next question. There are two ways one should think about it, or maybe three ways. One is a brute force method. That is, You grind it, spend a lot of energy, use that as a filler material. The other is use this as fuel, but that generates a lot of greenhouse gases and what have you. What we are saying is, you heat it just to the point of Tg, somewhere there. Soften it, don't melt it. That's the word. Somewhere around Tg. What did I tell you before? There are only three things: time, temperature, pressure. When I have a judicious combination of these three, anything can be done, right? That is the soft spot we are trying to find. Okay, now we heat it for X amount of time. We infuse it after it is softened, with a particular polymer that would react with the softened thermoset polymer under pressure. So I completed all three: time, temperature, pressure. And that will give you, and we got products that have been but I must admit, my statements sound lofty. All I have done was at a coupon level. I have not extended this to a component level or a system. So I want to qualify. But there are others I read recently are doing this kind of a thing. Maybe I forgot the names, maybe they are ahead of us. But it's going to be possible fairly soon, no matter what. But it's a little bit more involved. So, if you have any other item,
So you have produced timber which has equivalent performance.
I have produced what?
Timber which has performance equivalent to steel.
Right.
How have you done it?
Okay. Same, think of it along the similar lines. What did I tell you? Timber has two ingredients: lignin, which is the resin, and cellulose, which is the fiber. So, first of all, we want to typically timber has about 25%, 28% of moisture. We equilibrate it around 18-20% there. That's right? Okay. So what we want to do is the following. We are finding a resin that is compatible with lignin. So we warm it, not heat it. I don't want to have an ignition going, right? Therefore, I warm it, let some of the air escape, and infuse the polymer that I'm talking about to have a bonding, covalent bond with lignin. In this process, I'm also compressing it so that not only my voids are filled because I removed some air, and then I am going to make the lignin react, and then I am compressing it. But you know what? The fourth item, what I am doing? The polymer that I am infusing is a respect to water. Therefore, I'm reducing the water content from say 20 or 22% to 12% or whatever. That 10% margin is reacting to with the resin that would polymerize the thing. I got a double advantage. That is, I reduced the water content, therefore I increase the strength. I've reduced the void content, therefore I increase the strength. I've compressed the wood, therefore I have increased the strength. Thus, I was able to obtain, do you get what I just said? Thus I was able to get about 30 KSI to failure.
Yesterday you told about the FRP bolts, like the tension in the bolt, it reduces after some time.
Repeat what?
The tension in the bolt is lost after some time. The tensioning which you do. So is it due to the softening of the resin or?
What does tensioning mean? It has some force. Obviously, this force has to be locked. Otherwise, it will go back to zero, right? When I lock it, what I have done? I've created a pre-stress. Then what I have done? I've created a creep problem. And then what I have done? I've created a local stress concentration problem due to the drilling of those or creating those threads. So all these, it may not lose overnight or in 2 days, but I can assure you it will lose almost back to zero in a month or so because of all these reasons. And more importantly, I told somebody, that gentleman there, Keshav, is that your name? Okay. I told him, never ever cut an FRP rebar because you are cutting the cable, fiber. And then you are left with only the localized stress resistance offered by resin, which is very low. Anything else?
So without cutting, how can we adjust the length and also?
I wouldn't even go near that. I wouldn't even think of cutting it, period. You're wasting your time and money, you know. No, you don't even think about it.
Just order as
Oh, we have to order what length we have.
you need.
Yeah, I wouldn't even think about it. No.
The dimensions cannot be altered in any case.
See, a manufacturer telling you, I'm glad. You see, he just graduated from college. Why did I say? You wait 5 more years, you will see how he is going to be transformed.
Sir, when we are using eco-friendly formworks or panels, is there any recent change from GFRP bars to this? Or it's our basis on their criteria?
Formwork, you said? Did I hear?
Eco-friendly panels.
Right. What is the definition of a eco-friendly? What is that? It is that if you use conventional resin system, you cannot recycle it. That is not a eco-friendly. So, if you want to have a eco-friendly panel, there is a resin known as PFA. You can try that. That comes from wood resin, you know. That is eco-friendly. Now, what I don't know is, I haven't done any work with that particular, my colleague did, with the guy, my co-author, Gupta, did some work. We can talk about. I think it is expensive. That's a wood-based derivative or any plant-based derivative, you know. So I want to throw a challenge. That is, India keeps talking about pollution, especially in the northern states, coming from burning of what they call stubble, right? So the question is, how can we make a foam out of it and use it? That is where the innovation comes, you know. I tell the parents, You send your kid to a branch that is most unpopular today, so that when he is ready to graduate, that comes into maximum demand. I mean, that's a statement with a tongue in the cheek, but that ought to be the philosophy, you know. So how do you think about it? It shouldn't be so difficult to come up with forms that can go into a variety of panels. It doesn't have to be housing. There are many other cases where you are solving many problems. The future,
Insulation purpose.
that's one part of it.
Noise absorption.
Right. The thermal insulation, the noise insulation, all these one part. But more than that, if you juxtapose it in a manner with the shell, you can increase the strength, stiffness aspects of it all, and you don't have to use the non-eco-friendly thing. Thank you.
Sir, your thoughts on modular prefab units. So what is the cost of that, sir? If we want to construct some 1,000 square feet.
What is what?
Cost.
Cost.
Of the PFA.
Oh. Cost. I'll tell you this. I have my cousin, a professor in business school in US, you know. So I asked a similar kind of a question. That is, hey, I'm developing these things. Is it okay to say I will have a 10% profit? That's me, I stated to him, 10% profit. Like all the costs, you know how all the different costs, right? You add them up. So I said at the end of it, 10%. You know, his immediate answer is, that's a stupid way of thinking. That's what he told me. Okay, why? Cost is a supply and a demand issue. These guys will drop the cost by 10, 15, 20% the minute their supplies are not moving. Okay, anyway, that said, I'll tell you the cost now. We believe that the geopolymer panels building that we are constructing now may be about 2/3 the cost of a regular construction for housing. That's too broad a statement, but it has other parameters associated. Well, I won't go there, but that's about a thumb rule based response to you. Am I making sense? Yeah, that's thumb rule.
The same concept, the same concept of your building which you are making with FRP. So I think already IIT Chennai they are done with FRG. Fiber reinforced gypsum panels 10 years ago. I think they constructed a multi-stored building which cost around 10 to 12 lakhs. Same concept, but they used FRG panels, gypsum panels.
Gypsum.
Yeah, fiber reinforced gypsum panels they have used. IIT Chennai campus itself they constructed I think 4 to 5 buildings.
Very good.
10 to 12 years back.
Sir, in the Athon type ramped up building, is the rat issues?
It is what?
Rats.
Huh?
Rats.
Rats.
Huh?
Rats.
RAT?
It can enter into the earth.
No. These are rammed earths. They're compacted. That's what the meaning of rammed earth, you know. Oh, no. There's no such thing at all. These are.
Having is done manually.
Huh?
Manually.
That is why I said that is not a very mechanized system. You see, it could be done, but
Because it is done in rural areas.
in the rural areas, that's right. Yeah. No.
I think the cost is a prominent factor.
Again, for rural labor force, rural material, this is not for a mainstream thing, remember, not for urban areas,
Minimal uses of resources.
Yeah. So there are a lot of challenging issues. I would like some innovations done as opposed to, you have to do conventional things as well to make some money, right? We understand that. Nothing wrong in making money. But you make it, with innovation, that's even better. This message is for the guys who are manufacturing things, And even in the designs, you have a lot of fantastic innovations you can make, The question is, how you interact, you meaning we have university type people, we have industry type people, we have government type people, we have investors. So how you put the coalition together to make it happen, that is a challenge.
Yes.
Always it is. Nobody wants to believe anybody. That is the kind of a times we are in, right? So if you tell me the sky is blue, I had to scratch my head. Did he really mean it is blue or something else? So that is the state of mind we are in,
And to go along in the innovation sector, that is
even tougher. Right. Immediately you say, if it fails, the guy is corrupt, that's the other side of the coin. So nobody wants to take a chance. But that's where we need to overcome that suspicion, both sides. Research is not an easy business, 9 out of 10 times. I only talked about successes. I never said a word about failure. I had a lot of failures, let me tell you that.
codes even have so much gaps.
Huh?
The code,
Yeah.
it has so much gaps.
That is because we don't have enough information from the field. Unless we get a lot more info from the field, there is no way we can fill those gaps. But you said it right. We struggle with that too. It's not that but at some point I had to put this into practice, right? However crude it may be, however uneconomical it may be. So that's why we are really soliciting your inputs in terms of what is lacking, where is lacking, what needs to be modified. We are really soliciting that information.
And ultimately, on a positive note, it's a big opportunity for us.
Oh, it is. Look, it's a big opportunity for everybody
In GFRP.
in a country like this where you have a housing crunch. If you can revolutionize the housing and reduce the cost, there's nothing like it.
Marvelous.
Sir, actually, persons also, I don't know how to contact, who to contact. So, some 4 to 5 years ago, not related to FRP reimburse or something, okay. Some ASTM code, we have had some clarification or some kind of challenge when we had been doing some experiments. Actually, we dropped an email to the ASTM concern guides, but no one we have responded.
You let me know, you send me an email, I'll make sure.
Not at all relevant to this.
Understand.
Some tests related to composite materials.
You
from
see,
ASTM standard.
please look, we are also busy. We cannot simply sit and wait to get questions and respond to it. Remember that, please. So ASTM, the whole thing is done on a pro bono basis. They don't give me a dime to serve on a ASTM committee. They don't even give me my travel allowance to serve on an ASTM. Leave aside. No, my point is, sometimes it happens, you may have to. That is why meeting people one-to-one, since I know you personally, I respond. But there are a lot of emails I don't respond either, you see. That's why developing the personal relationship helps.
At that time, we wrote on behalf of someone wrote on behalf of our company. So, but we didn't get any response from clearly.
No, it happens. I'm not contesting your statement. It happens. We know that it happened with me. I forget about somebody else. I'm talking about myself. So, what can we do? We only have so many hours in a day, and we do our best. Leave it there. That's all I can say.
Sir, any Dex Lab design available in that manual? Dex Lab?
Any what?
That in the manual, essay manual, Dex Lab design?
Oh yeah. Of course, absolutely. I did the one-way slab design. You can follow that. Same kind of a thing. Yes, the answer is yes.
Sir, one question from online participants. So they are saying that as GFRP we can't maintain site. So what will be the development length if we are using?
Well, I gave you the equation for development length. Please follow that. They're all in those 300 slide package. Yeah. Those are very valid. If any, they are on the very conservative side. In other words, even if you reduce it by 20-25%, you're doing well. Primarily focus on the development length only on the tension side. Don't have to worry too much about it on the compression.
Because sir, you are doing this is from all of the participants, and we are very grateful.
I don't know. Sometimes.
We can understand very complex topics very understandable, and it is it's a privilege to learn from sir. And
I make some provocative statements once in a while. That's on purpose to stimulate the thinking, right? Thank you.
So this is the last lecture of Professor. So all the questions are done. So I'll ask Dr.
This is Vishwanath. I'm a faculty from Mechanical and Aerospace. I was a BTech with Civil, but I moved on with Aerospace and other things. But it was very nice, and I would really thank you for coming and sharing your decades of experience in a capsule. I think it would have really benefited the entire community.
Thank you.
And I can see that within half an hour you are engaging them with the questions and other things. It tells that how seasoned teacher you are.
Thank you.
It's really great to have you, sir.
Thank you.
And on behalf of Professor Surya, I would like to give.
Oh, thank you. Thank you. Just to share with others. It's not for me, it is a collective gift, I remember that. So, even though I'm of Indian origin, so I never understood initially when I went to America 60 years ago, when people opened the gift, I didn't quite relate it. You know what I mean? So I also guide a lot of students in mechanical engineering. Yeah.
One picture with you.
Sure. Oh, absolutely.
Yesterday I missed it. Thank you, sir.
Yeah. Her grandfather was a Vedic scholar, got his degrees from the institute we run in Rajahmundry. The next Shankaracharya for Kanchi was selected from the institute where he graduated, and we guide it in Rajahmundry. The new one, the new one.
This is the pen.
Wow.
Yes, why not? Of course.
Oh, wonderful. Absolutely wonderful.
Will be in your memory.
That's, thank you. Thank you. Thank you. Thank you all. Sure.
Go sir, please come faster.
Thank you.